Good afternoon, I am Mr. Ish. Very recently, I presented a video on the basic applications of Euler's formula, and primarily the focus of that video was the derivation of this formula you have right here on the top, the Euler's formula. Anyhow, in this video, we're looking at some more basic applications, just expanding on some of the basic ideas we presented in the previous video. The applications that can arise from this Euler's formula. Remember, in all instances here in this top formula, the theta can be easily replaced with the x variable. Anyhow, we have the formula written over here. I've just presented two additional items here. Complex number, as you remember from precalculus, is equal to x plus yi. You can convert that into the polar or the trigonometric form. You have the r, which is the modulus, the theta, which is the argument, and that can be rewritten here in this form. If this is equal to that, you can substitute this part right here for that, and you can derive this formula right here. This part specifically can be shown to be true from the identity on the top. And then if you replace the angle theta with the y value and you multiply this complex expression here with the exponential base, you can come up with this additional formula, which we will show how you use that in this video. You have this ex times e to the iy, the laws of exponents. These add up, they're all equal to a complex number, which when you expand it becomes that. Let's start with the basic applications and we'll just dial things up a notch a little bit. I don't want to present a very long video over here or intimidate anyone. We'll just start with basic ideas and just see how everything goes from there. Our first one will be related to this expression here at the very beginning, how we can convert this into a complex number. We have here 5i pi over 4, e to the power 5i pi over 4, which you really can write as ei and then 5 pi over 4, because this tells you exactly what the angle here is. 5 pi over 4 is 225 degrees. A 45-degree angle in the third quadrant, which if you remember in terms of reference angles, the sine and the cosine values will be equal, but they'll be both negative. You'll have here cosine 5 pi over 4, right? And then you'll have plus I sine 5 pi over 4. See, we have something which looks like this, and now we're breaking it down into that form. And you'll have minus 1 over root 2, and then minus I over root 2. And this right here would be your answer of this expression right here, and that right there is your answer you would present. Let's look at another e, and then we have I 3 pi over 2. Some would write as 3i pi over 2 or 3 pi I over 2, it doesn't matter. We're basically looking at angle here 3 pi over 2, which is 270 degrees. So you can do cosine 3 pi over 2 plus I sine 3 pi over 2. And you know you can work on this. Cosine of this 90-degree angle, which is a reference for 90, is going to be 0. And then here the sine of this is going to be a minus 1, but it's going to be a minus I. So all of this expression right here will give you that in terms of your answer or your output. It's minus I. Not too bad. How about we look at one more of these basic ones, and we look at something which is this e, and then we can say 2i pi. And here what we're going to be basically looking at is ei and then 2 pi, and you know that's cosine of 2 pi plus I sine 2 pi. And you know 2 pi is 360 degrees. Cosine of that is a 1, but sine of that is a 0. I over here, which is just a 1. So e2i pi is going to give you this in terms of your output, and this one is done as well. Now we dial things up just a little bit. We have something which looks like this, and when we're looking at something which looks like this, here's our question. We're thinking of something like that. Let's just say like this. We have something which looks like this, multiply with something which looks like that. We basically had e squared times ei pi. Think about it. Same basis. When you multiply and the exponents add, you end up with just that. E squared will just sit outside on its side, and then you'll evaluate this as you would this part right here, and you do cosine pi, and then you do plus I sine pi. So when you see an expression which looks something like this, you have to separate into this, because this part will sit outside, pushed away, and then this part right here, you'll follow it exactly with this scheme you have here on the top, like you have been doing in the first few questions I presented here earlier. And this you will evaluate it. It won't be hard. E square cosine pi is a minus 1. All of that will zero out. You'll have equal here a minus e square, and this right here would be the output value of something which looks like that, minus e square. So this is here just us getting comfortable with some of these Euler's applications, and of course things get harder, but as you go into calculus 2, calculus 3, everything gets harder. But we have to start always with the basic fundamentals before you get into that zone. Let's look over here, e1 minus, and we'll do here pi I over 6. You know this is not going to be too hard. You're looking at something which was what? You know you're bringing a minus over here, so that's complicating things a little bit. You're looking at something which looks like this, e to the 1. And then you're looking at something which was e pi I over 6, right? Because when you have similar bases, the exponents subtract. You can do everything here as you would like that. And then here you evaluate this as cosine pi over 6 plus I sine pi over 6. Not too bad over here. And then we have this e sitting here on the top, and then we evaluate this. Pi over 6 in terms of a 30, 60, 90. Here's my 30. Cosine of that, you can have here a root 3. Here you'll have a 2. Here you'll have a 1. Cosine pi over 6 is going to be a root 3 over 2. And a sine pi over 6 will be 1 over 2, will be I over 2. You can do a good common denominator over here. You'll have a root 3 plus I over 2, and this 2 can flip and it can attach with this e on the top. So your answer would be 2e, and then we'll have root 3 plus I, and that right there would be the answer of this expression right over here. And you know, just for a little clarity, we'll rewrite it here, 2e divided by root 3 plus I. That right there is my answer. Let's look at this one, e to the power of minus 1 plus 3i pi over 2. Again, just separate them out. It's no different than you looking at something like this times this right here. Because here, of course, similar bases, the exponents add minus 1 plus that is just that. You know this e to the minus 1 will really come out as 1 over e. Then you're really looking at cosine, because you're bringing this part here. You're looking at cosine 3 pi over 2, which is easy, plus I sine 3 pi over 2, which again is easy. And you're looking at 1 over e. Cosine of 3 pi over 2 is a 0. But this right here is a minus I. So you're looking at a minus I over e. And that right there is your answer or your output for this expression over here. And it should be right. Alright, let's focus in on this e to the power of 1 plus I pi over 4. You know we're looking at something of this form right over here. You know you can separate this out into this, and it's not hard. This angle pi over 4 is 45 degrees. It's easy. This combined will give you very well that. You'll have an e sitting out, then you'll have a cosine pi over 4 plus I sine pi over 4, and all you'd have to do is just open that up by bringing in the numerical values there. Pi over 4 cosine and sine are the same. It will be 1 over root 2 plus I over root 2. If you want, you can leave the answer as this, or you can open this up and apply the e in a distributive format. You'll have e over root 2 plus ei over root 2, and this here could be a good answer for that expression which you had right over here, and the answer would be completed. Let's give this one a try. We have e to the power of 3 plus 2 pi I over 3. If you want, you can rewrite it as this just for more clarity. E to the power of 3 plus I 2 pi over 3. You know you're looking at a addition of two separate exponents which came from the same base. We have e cubed, and then we have e I 2 pi over 3. You could very well just push the e cube out, and then you're looking at a cosine 2 pi over 3, which you know is a 60-degree angle, but in the second quadrant it's 120 degrees, plus I sine 2 pi over 3. And you know it's not too hard. You have e cubed just sitting outside, and you know cosine of 120 is the same thing as cosine of 60, but in the second quadrant it will be a minus 1 over 2. Sine of that, you know, will be plus I root 3 over 2, because sine is always positive in the second quadrant. If you want, you can open up and distribute e cube across, and there's nothing wrong with doing that. Minus e cube over 2 plus e cube I root 3 over 2. Here is a relatively good answer. The only reason why I'm saying relatively is because some people may not have opened it up and some people would. And if you wanted, you could even just put the I out on the other side. Or if you want, you can even express this specific form right over here, just this second part, as e cube, and then you have an I root 3 over 2. You see how the e cube is kind of outside the denominator, it's not sitting over that over 2. But either way, it's all good right over here. For this next set of questions, we'll see how we can do a little bit backwards working over here. We have to convert this. These are the form of questions where you have something in the form of x plus yi, right? X plus yi right over here, and you have to convert this into that form right there. Something which would look something like that. Alright, and it's not hard. You have to now come back to this modulus and argument, and that's exactly what we have to do. You're looking at here something which is really root 3 comma minus 1 in terms of its plot on a complex plane, which you know would very well put you in the fourth quadrant. you would do this square plus this square root. You'll do root 3 square plus 1 square. You could put a minus 1 square, but I'm not, it would be irrelevant, and root of that, and you know you'll get a 2. So here your r value is 2, and your argument would be what? You would be just doing minus 1 divided by root 3 inverse tan. Remember, the argument is always your y divided by your x, your y component of your complex number divided by x component of the complex number, and you do inverse tangent of that. But we don't need to do that because we know exactly these are trigonometric ratios coming into the picture, root 3, 1, all of that. You know very well you can do just right here 1 minus divided by 3 root and inverse tan it, and I'll get a 30 degrees minus 30. But since I'm in the fourth quadrant over here, right, I'll be thinking of 330 degrees. 330 degrees would be what? 11 pi over 6. So when I'm writing this into this form right over here, re to the power of I theta, I'm getting here 2 e to the power of I, and then theta is 11 pi over 6. If you want, you can write this again as 2e to the 11i pi over 6. You don't have to, you can flip around with these letters if you want, but this right here is just as fine, and that right there would be your answer. 2e to the power of I 11 pi over 6. What we can do now is let this next question be the last question of this video, because again we're keeping everything basic, but we're showing the variety of applications from this Euler's formula and from these two additional items I've presented you over here. We're looking at something which looks like minus 5i. Alright, maybe I can present another one after this, but we'll see how this one goes. You know here very easily the r here, the modulus will just be a 5. What will be the angle over here be? You're looking at minus 5i, but you have to convert this into x plus yi form. You're looking at 0 minus 5i. And you know when you're thinking about this, you're looking at a 3 pi over 2, because that's how you generated that negative over there. A sine of a 3 pi over 2 or 270 would have generated that negative, and that's how you got that. So all you gotta do is now put this into this form right over here. You have a 5 over here. Remember, the modulus here is 5, not minus 5. And then you have here a e, and then you have an I, and then theta, which is 3 pi over 2. It's the effect of this 3 pi over 2 which would have brought that negative over there. So do not make the mistake of putting a minus here, because generally the formula would have been x squared plus y squared, and then you're rooting it, right? In terms of determining that modulus, you would eliminate any negative, because you cannot do a square root of a negative number. But this answer right here is true, and it's good. We're going to do one last question, and why not? Let this last question be here. Z is equal to 3. You know you're looking at 3 plus 0i, but here in terms of your modulus, you know it's 3, because this square plus this square, the root of that will give you 3, and your angle over here could have been generally 0. It can also be 2 pi. I would just stick with here with 0, because we want to express things always in the more simplest format. There's nothing wrong with you doing that. With regards to this idea over here, you'll have 3 e to the I 0 degrees, or if you want you can do 3e to the I, you can even bring in a 2 pi over here, because it'll generate you exactly the same answer, and this right here would be it. But if you're going to go with this answer right here, you might as well just do 3e to the 0, and you might as well just do 3. So you can see there's a variety of ways you can express this right here, but you can see this answer here is fine, this answer here is fine. You can even present it in either of these other ways. And with that, let's end this video. Thank you for watching. Stay tuned. Have a nice day.